Right, good morning, everyone. Hope you can hear me this time. I've got headphones on here. This last time there were some audio issues. Um, yeah, so again, today I will be at the blackboard. So I have a mic here in the headphone, which is better since I'm away from my laptop. Okay, I saw your lab reports. Not many people have done in lab 3 and 4 so far. And that's why I'm not graded them because it's too few right now. So lab 4, yeah, so lab 5 is due tonight. Lab 4 was due last week. So not many people have turned them in. So, turn them in ASAP. Also, we don't have class next week because of fall break. We have fall break from October 9th to 13, and 13, I believe, is, let me make sure. Yeah. Wait, it's, I think, 9 to 12, not 13. So 9 to 12. And well, 12th is next Tuesday, which means we don't have class. So next time we'll meet will be a couple of weeks from now. And the next lab, I think, is a simulation. The lab after that is a simulation, very simple. So not much to worry about. We can even combine those labs if it turns out we don't have enough time. But it should be fine. So we don't have lab next week. So right, lab 5. If you guys have any issues with lab 3, 4, or even 5, where you have take-home stuff, you should let me know. And you can be here. Some people have been in the lab, and most of them have had their issues resolved. So if you have issues, you can let me know so that I can call you here, and we have equipment here that will help you. So if you're not able to turn in your lab reports because of that, just let me know. Okay. Other than that, I think we can begin lab 6, Kirchhoff laws. Again, the document is on Blackboard. I think so. Yeah, lab 6, Kirchhoff laws is on Blackboard. So download the document, and for this lab, you don't have a take-home part. So we'll just directly move on to the experiment. I'll explain how it works, and then we'll again. So today we just have one experiment, not like last time we had 3 different setups. It's just one setup today, so it should be quicker than last time. So, okay, I'll move my computer screen so you can see the Blackboard. Okay, we have Kirchhoff laws, double H. And some people pronounce it Kirchhoff. I think I looked at the official pronunciation. I think the word is, I believe it's German. So I think they pronounce it Kirchhoff. Okay, so Kirchhoff laws. We have 2 laws from Kirchhoff. The first one is Kirchhoff's current law, which says if you have a junction, and we talked about junctions last time, what happens, the current splits. So when you have a junction, let's say this is a junction, and you have some current arriving here, we're going to call I naught. And obviously, it will split into 2 parts here. And we'll call this I1, we'll call this I2. And when this happens, we know that I1 plus I2 has to be equal to I naught. The current is splitting, right? So we can say I naught is equal to I1 plus I2. And Another way of saying is I naught minus I1 minus I2 is 0. So the basically it says that at a junction, the sum of current has to be 0 at any junction in a circuit. That's the first, so that's called Kirchhoff's current law. So you can have like, here we have, three different currents here, the original current and the, when it splits. Current that is moving towards the junction is positive. Current moving away from the junction is negative. That's how the convention goes. So you can see I naught minus I1 minus I2 is 0. So that is his first law. Second law, the voltage law, states that the voltage drop in a closed loop has to be 0. So it basically says sum of all voltage drops, and k goes from 1 to n, it can be any number, will be equal to 0. And what does it mean? So we can draw a simple circuit here, and we'll put a resistor here, we'll put a resistor here. This is R2, this is R1, this is obviously our battery. Right, now the voltage, according to this law, the voltage drop has to be 0. Now this we know will have some voltage. This is a power source. So we're going to call it source V sub S. And from Ohm's law, we know that the voltage drop. So, the voltage drops when you have an object, especially like a resistor, the voltage will drop, which means that V has to be negative, which means, and you can call this current I that is flowing through a circuit. So I into R1, that gives us the voltage drop from the Ohm's law. So, and we have a second resistor here. Again, it will be negative. This has to be equal to 0. And another way of saying it is R1 R2, take that to the other side, and R1 plus R2. And because they are in series, that gives us the total resistance. And again, we get our Ohm's law that we know. So IR1 voltage drop across this resistor, IR2 voltage drop across this resistor. They are negative because their voltage drops. So the voltage drops, that's why they're negative. This is positive because this is a power source. So in a closed loop, the voltage drop has to be equal to 0. That's his second law. And we'll use these two concepts today to discuss what we call a Wheatstone bridge, which is a setup we use to very precisely find an unknown resistance. We have 3 known resistance, and we can find the 4th one very precisely using a Wheatstone bridge. So these are the 2 things we're going to use. So yeah, if you want to note this down, you can. I'll move to the Wheatstone bridge. So the setup is a little bit different. It looks different, but the circuit connections are going to be exactly the same. So we have this is what we call a Wheatstone bridge. You have 4 resistances here, and we'll call this R1, R2, R3, and Rx. This is the unknown resistance. We know 3, and the 4th one is unknown. This right here is a galvanometer in the middle, which we used last time. So it tells us how much is the current changing. So it tells us the deflection, and we'll call this junction A, and we'll call this junction B. Right. Okay. Using second law here, and we're going to use this right here. So what we do in a Wheatstone bridge is we balance the bridge so that there is no deflection here on the galvanometer. No current is flowing through here. So there it's perfectly balanced. And when that happens, it means the voltage drop across this will be zero since there's no current. And what that means is if we take this loop, so we're taking and we can, so the loop, this loop with the R1 resistor and the galvanometer and the R2 resistor. If we take this loop, what do we get with the second law? We get I1 R1 equal to I2 R2. And current here flowing is I1, current here flowing is I2. This makes sense, right? They're in opposite directions. That's why they have opposite signs. If you bring this here, it will have a negative sign. So voltage drop in this loop has to be zero. So we get this relationship from this loop. Similarly, and right, since basically because this is balanced, no current is flowing through here. We already know that the galvanometer shows zero. So I1 goes here and I2 goes here. Now using the same relationship in this loop now with Rx, R3 and the galvanometer, we get I1 Rx, I2 R3. This only happens when the bridge is balanced. So when G gives you zero, basically bridge is balanced. And what does this give us? We can, well, divide the two equations and we get this relationship. Rx over R1 gives you R3 over R2. So I divided this equation by this equation. That's it. You had I1 on both sides, so that was that obviously went away. I2 from both sides went away, and we get this relationship between the four resistances. So if you balance the bridge, you can find the unknown resistance if you know the other three resistance. Now, the setup we are using, obviously, for R1 we use a resistance box like last time. For R2 and R3 we're using a wire. So we use a wire and we change the length of the wire. Total length of the wire is 100 centimeters. So it's 1 meter, the total length of the wire. And which means, and you have like a slider which can change the length. So it's like 1 meter wire and you keep changing the length. And this, the wire from here to here would give you R2, this, and wire from this point onwards to the other side will give you R3. And you can slide, you can change this point and you can keep moving this point. And because it's basically the same wire, and how do we find the resistance? Well, we are changing the length. You know, resistance depends on length. So we change the length. Actually, I can do this here. So let's erase this part. All right. So R3 over R2. These are the two. R1 is a resistance box. R1 and R2 is what we need to find, which is a wire. So R3 over R2, right? And well, we know first of all that R is equal to rho L over A. So if you use the same concept here, you're gonna get, well, the rho will cancel out because it's a resistivity and it's the same wire, same material. So rho is gonna just get canceled out, we can write it in and it will cancel out. So row, the length, we're going to call it L3. What is it in your, I think in the, I think in the document that I've sent you, the length of R3 is L2, not L3 for some reason. It's a bit weird. So I think in the document is L2. So I'm writing L2. And yeah, over A2 or row L, and the length of R2 is L1. So make sure you don't get confused. L2 is not the length of R2, it's the length of R3. L1 is the length of R2. That's how it's in that document for some reason. So I'm just being consistent. Again, this cancels out. And what you get is yeah. So you get R3 over R2 is L2 over L1 into A1 over A2. But the thing is, it's the same wire. We're just moving that slider so that we get different L1s and L2s. So we're basically changing this R1 resistance box, and we want to look at different points because again we are doing four trials for each wire, for each spool of wire. You'll see in the experiment. But we are doing 4 trials, so we just want an average value again. And we'll change R1 10 ohms, 9 ohms, and then we have to find the balance point. We'll move that slider for R1 and R3. We'll look at different points to get an average value. But it's the same wire. We're just changing the length. So which means the cross-sectional area will be the same because it's the same wire. So this also cancels out because A1 is equal to A2. So which means R3 over R2 is L2 over L1. So if you know the length, you also know the resistance, well, the ratio of the resistances, and that's all you need to know. You just need to know R3 over R2. You don't exactly need to know R3 and R2, just the ratio. And the ratio can be found from the length. And R1 is a resistance box, obviously, so we already know what R1 is, and then you can find Rx. So this is the Wheatstone bridge setup, and this is a circuit diagram for it. There's also another circuit diagram which actually tells you what's happening here, and I will show it to you now. So this is what we are doing today. All right, so you guys can go with this, look at this, what's happening, and I'll take a couple of minutes to make sure that everything is all right. The setup is working. So yeah, you guys do that. It will be a couple of minutes. Okay, so I'm going to take the camera. All right, you can see we have the galvanometer, we have this uh, resistance coil, and it has 5 different spools, uh, and they are all different than one another. They are different wires, sometimes different material. So we're going to do it for 3 spools: number 1, number 2, and number 5. I think that's in your document as well. And we're going to do 4 trials for each of them. And this is the meter bridge, and you can see this. Okay, so yeah, this this has to move, so we can move this slider and change the length of uh, R3 and R2. Now, I think if I look at the setup, yeah, R2 has to be this side. This side will be R2, and this side will be R3. So I will give you the values and note them down. You will do the calculations. So if you look at the document for spool 1, the material is copper, and it says it asks you for the gauge. The gauge is 22. The gauge is 22. You have to note these things down. Gauge is 22. Length is 10 meters. The length of the spool is 10 meters. And the gauge is 22, which means you're going to have to look this up, what gauge 22 means, and find the diameter of that wire. And from there, you will find the area. So gauge 22, and now you have to look up what gauge 22 means. So we can do the first spool. Right now, as you can see here, it's connected to the first spool. This is the first spool right here. So it's connected to these 2 terminals. Okay, let's see. So it's already connected. Everything's connected correctly. We have a rheostat here as well. Again, protect the circuit. And so we'll change the resistance, and the R1 needs to be pretty small for this. We'll start with 10 ohms. So resistance box is already at 10 ohms. And we're going to change the length now here. So the total length, remember, is 1 meter. It's 1 meter. Let's see. Gets to 0. Not here, not here. Here. After a point, it stops moving. When it gets to 0, it can't go negative. So when does it get to 0? We're on here. So for the first spool, R1 is 10 and L1, which is the length of the resistance R2, okay, let me confirm if this is, hold on, let me see the connection. This is R1, R2. Yeah, this should be L2. That side should be L2. Smaller side is L2. Okay. All right. Seems like L2 is this side because it's connected here to the rheostat directly. As you can see on the circuit diagram of the Wheatstone bridge, the side that is connected to the rheostat, it will be L2, and the side that is connected to the battery will be L1. So L2 is this side, the smaller side. And what I'm getting here, I'm getting 0 at, this is what? 1, 2, 3, 3 centimeters. So yeah, the length, yeah, L1 is 3 centimeters. L1, which is the length of R2, is 3 centimeters. And again, you have to convert it to meters, and then you'll find the length of L2, which is just 1 meter minus whatever L1 was. So L1 for 10 ohms is 3 centimeters, 0.03 meters. Okay, let's look for 9 ohms. So the second measurement we're doing it is at 9 ohms, and they will be pretty similar. Hold on, it's just going back. Yeah, yeah, you have to find four different RX. I'm just thinking of the circuit and thinking of which side is R3 and which side is R2, because try to make sense if the calculations work or not. Three, four. Yeah, you'll find Rx for each reading, and then you take an average value, and uh, you'll find the resistivity. Yeah, that's what I'm looking at. It says L1 is 1 meter minus L2. Well, that can also be written as L2 is 1 meter minus L1. It's the same thing, but because both of them added will be 1 meter, so you can write it anyway. But I'm just trying to think which side is L1 and which side is L2. That, if not done right, can mess everything up. Obviously, one side will be L1, the other one will be L2, and if your calculations don't make sense, then you will do it the other way around. And if you get it right, you will know that was the right one. But I'm just trying to think. Hmm. Right? Why? Oh, I think it's because the way I have the circuit, I'm looking at circuit diagram, I'm looking at what I have here. It's because the rheostats to the right in the circuit diagram, but here I have it to the left, so it's kind of opposite. Just the rheostat is connected here. This should be L2. L2 should be smaller. So I think I told you to write L1 as 3 centimeters, was it? For the first one, it is L2, which is 3 centimeters, not L1. It is L2, which is 3 centimeters, and then you can find L1. It's just 1 meter minus whatever L2 is. The 3 centimeters is 0.03 meters. That's L2, not L1. So side is this side is L2 and this is L1. Okay, so now it's clarified. Now we can move on. Let's do 9. And this time should be slide. So it is, I'm getting 6 centimeters for L2, 6 centimeters for L2 in the second, which is at 9 ohms in the second reading. Now we're doing 8. And at 8 ohms, the length of L2 is 8 centimeters. 8 centimeters. The next one is 7. Uh, this should be higher one. This is 10, 10, slightly lower than 10. 9 actually. 9 centimeters. For 7 ohms, it's 9 centimeters. So we have 10, 9, 8, 7. Those are 4 readings for R1, and we get 4 different lengths of L2. And you will find L1. From that, we know L2 over L1 is R3 over R2, and we know R3 over R2 gives us Rx over R1. So you know R1, you can find Rx from these 4 different readings. What was L2 for 8 ohms? 8 ohms. I think it was 8. I think it's 8 centimeters. Right. So Rx, you can find an average value of Rx, and then you have the resistivity. You can find the resistivity because now you have the area. You have the gauge. You will find the area from that gauge, and you can then find the resistivity because now you have the length, which is 10 meters, which was also given to you, and you can find the resistivity. And obviously, you have been given the correct resistivity here, 2.18 into 10 raised to minus 8 ohm meters. And then you'll find the standard deviation. What is the standard deviation? Standard deviation? Why is the sigma there? What does it even mean? Yeah, I think they just want the error percentage. It's not standard deviation. Yeah, they just want the error percentage, no standard deviation. I don't know why they have sigma. It's just the error between those two values, whatever you find and whatever is written there. Somebody asked AWG or SWG. Well, I will look that up later after I finish this up, and then yeah, we can look at that. So I'm moving from spool 1 to spool 2. We'll do the same thing. So now we have spool 2, and the gauge for that is 28. The gauge is 28. The length is again just 10 meters. Length is 10 meters, but the gauge is now 28. Again, it's just copper. And yeah, let's look at the values for that. So again, it will be 10987. We'll keep repeating that pattern. 10987 will be the values we'll look at. Okay. So the value of L2, so we're just finding L2s now. You can find L1 later, is 17.4 meters. It's wait, when did it go zero? Yeah, 17.4 meters. So 17.4 meters. Centimeters, 17.4 centimeters. I am messing up everything today. 17.4 centimeters, which means 0.174 meters. So 17.4 centimeters. All right, next one is 9 ohms. So let's look at that. 4, 3, 2. Yeah, 4, 3, 2. That's right. And the correct reading is it's 19.8 centimeters. 19.8 centimeters for 9 ohms. That's the length of L2. Let's look at 8. So for 8, I need 4, 3, and 1. Okay. 21.2. 21.2. L2 is 21.2 centimeters for 8 ohms. And final one, 7 ohms is 4 and 3. It's 23.3. It's 23.3. 23.3. So though that was for spool number 2, which is also copper but a different gauge. So it's 28 gauge, length was 10 meters for the spool, and now you can find the resistivity from the average resistance that you got. You know, the length gauge will give you the cross-sectional area. And then again, you will compare it to the actual resistivity of copper. So that was spool 2. Now we'll do spool 5, which is copper nickel alloy. For this one, we have gauge 22. It's gauge 22, and length is again 10 meters, but it's copper nickel alloy. And the thing is, I don't think they've given you the resistivity for that. They say you have to check it yourself. Okay, I will let you know what the resistivity is. I will let you know that. You can find the diameter and area, that's easy, but I will give you the resistivity that you need to know, because copper nickel alloy, we don't know the percentages, so it will vary. Okay, I will look at that. But the gauge is 22, length is 10 meters. And then again, we look at 10, 9, 8, and 7 ohms. So at 10, this is going to be big. Okay, now. Uh, 58.8. Length of L2 is 58.8 centimeters for 10 ohms. 58.8. For 9 ohms, it is 4, 3, and 2. It is 62.8. 62.8 for 9 ohms. 62.8 centimeters. Now 8, so 4, 3, 1. It is 65.1. 65.1 for 8 ohms in centimeters. Everything is in centimeters. You have to convert it to meters. And for 7, so just 4 and 3, we have 68.1. 68.1 for 7 ohms. So, okay, we've done all the 3 spools now. You know the gauge, you know the length of each spool, you know the values for R1 that we have used, you know the length L2. L1 is just 1 meter minus L2. So yeah, convert that all the lengths to meters. Then you can find Rx using the relationships that we discussed in the beginning. From there, you will find an average value of Rx from those 4 values, and you'll find the resistivity since you know the length and the cross-sectional area from the gauge. And then you'll find the error difference between your value and the actual value. 2 of them are here for copper. The for spool 5, it's not given. I will give it to you. I will put an announcement and also send you an email about that. But otherwise, I think this should be it. And someone asked for the gauge diameter. Do you want the SWG or AWG diameter? I'll also put that in the announcement. So you don't need to worry about that. You should calculate everything. You should calculate L1, Rx, the average value of Rx, the resistivity, and then the error percentage. So these are some of the things that you have to do. There are, I think you have some questions at the end. Let's just look at them. So yeah, right. You have this, and I don't know why it's 4.5 centimeters here. So yeah, you can delete that. It says 15 here. I don't know what, it shouldn't be there. So you can delete everything and just write down the values that we got. Okay, some post-lab questions here. Does the uncertainty with the standard? Okay, you do need standard deviation. In your value for Rx for spool 2 alone. Oh, okay. So it's not the error percentage. They do want you to find standard deviation, I think. Okay. Right. How many of you do not know how to find standard deviation? Is there anyone who doesn't know how to do standard deviation? Okay. Right. You will get an average resistance, obviously, but from that average resistance, we're going to get some standard deviation as well. And yeah, so you need to find a standard deviation, and then you're going to calculate the resistivity, right? And there are some rules to how you do that, because when you're multiplying numbers which have a standard deviation, or you add them or subtract them or divide them, they or maybe uh, take an exponential, so you need to follow those rules, because the standard deviations are what we call the uncertainty. They do not follow those same rules. For example, you never subtract the standard deviation. There are I think 5 or 6 rules was adding or subtracting or multiplying or dividing these standard deviations. So I will post a link on Blackboard. I think there's a good page which describes with examples how to calculate standard deviation. First of all, standard deviation is the equation for that. I can put it on the board, and so yeah, let me do that. I will put standard deviation, and some of you have calculators, and you can also do it online. How to do standard deviation? It's not that hard, but if you or just so you know, I will also put it on the Blackboard. So standard deviation, yeah, call it whatever. It's sigma square root of summation plus I from 1 to n. What does this mean? Okay, this is just an equation. What does this mean? You have a bunch of numbers. Let's say you have 3.3, you have 3.4, you have 3.5, 3.6, whatever. You have a bunch of numbers. You get different measurements, slightly different than each other. So they're not exactly the same. So we need to find what's the standard deviation, and what this is here. So you first find an average. That is this thing. X bar is the average. And what after you find some average of these numbers, you're gonna do, so it's xi, which is any one of these values minus the average, whole thing squared. So you're gonna keep doing that. So for example, well, what is the average of that? The average of this, I think, is 3.45. I think so. I think so if let's say the average here comes out to be 3.45. So that is X bar, and you will do 3.3 minus 3.45 whole squared plus 3.4 minus 3.45 whole squared plus 3.5 minus. So all the value, you have to do it for all of them. That's why we have the summation sign. So xi means any value from 1 to n. You have to do it for all of them. And over n minus 1, where n is the number of values that we got. Here we got 4. So n is 4. 4 minus 1 is 3. So n is the number of values, and you have to do it. You have to do this xi minus x bar squared for all of them here. So, and obviously you have the square root on top of all of that. This is how the standard deviation is found. And once you've got that, you write it as, for example, the average value is 3.45. So you will write as 3.45 plus minus whatever your standard deviation is. Let's say 0.01. So you write it like this. And it means that you have this margin where this is the basically your error. The actual value could be within that range. So this is your uncertainty. And all right. So once you have this, there are some rules. For example, if you have two values, if you have a couple of values, for example, let's take this one 3.45 plus minus 0.01, and you have another one 2.55 plus minus 0.07, and let's say this is, well, whatever, this can be centimeter. Let's just call these are some lengths that we got, and this is, well, this is A and this is B, and you need to do A plus B. So A plus B is pretty simple. You just add them up, which is 6.00. And plus minus, you'll also add these up. These are called absolute uncertainties, and you'll also add them up, 0.08. So 0.01 plus 0.07 is 0.08. But if you were to do A minus B, now 3.45 minus 2.55 is 0.90. But you're still adding them up. You cannot reduce the error. You are subtracting these two values, but you cannot subtract the error. The error is always going to be added. So it still is 0.08 centimeters. So and when you have multiplication, you have to first convert them into percentages. So for example, 0.0, what percentage of this value is 0.08? And what is 0.08? Well, 0.6, 1%, 1.3, 1.33. Yeah, so you can also write it as 6.00 plus 1.33%. You first have to convert them to percentage uncertainties from absolute, and then you add them up when you multiply. So if we have A multiplied by B, then, well, whatever 3.45 into 2.55 is, that is here, plus minus, you are adding the percentage uncertainties now, not the absolute. So 1.33 here, you will get something here, percentage, you add those percentages and you write the percentage, and then you convert it back to absolute. So this is how you do it from multiplication. Division, simple, it's the same. For division, you also do it like this, but again, you are not dividing, you are again adding the percentage uncertainties. It's the same, but obviously you're dividing these numbers, but not the uncertainties. So that's how you do it for division. There are a couple of rules when you have a power, when you multiply with a constant. So I will send you that page which will explain it much better than this. So yeah, it's complicated. It's something we do in physics 315, physics 1 lab. That is the first lab. We explain how this is done. Some of you, most of you will, I think, have had done that, but some of you haven't. So I'll send you that link. All right. Let's go back. What else is there? So okay, you need to find standard deviation of the resistance, and then you need to find the resistivity. And resistivity we know is resistance into area over length. So you're multiplying and dividing by some constants here. So you need to know how to do that when you have some uncertainty here. So we will do that. I'll send you that. Does the then there are questions, does the uncertainty in your variable power x for spool B alone account for how far we do this? Okay, you can add, these are what we have. X is pretty simple. Two spools of wire. Again, you can see here, it determines the resistance of spool 1 to be 19.8 plus minus 0.2 ohms. So this is the uncertainty, and the spool 1 to be this. Are these measurements consistent with the laws of resistance? So you will have to do, you will need to know, for example, so this, I think there will be spool 1, spool 2. So obviously you need to divide these two resistances to get that ratio, and you need to know how to do that when you divide. So you have to convert them to percentages and then divide those numbers, but you will add the percentage and insert these together for these, and then you will convert it back to absolute. It's important to have the final answer back in absolute terms, not in percentages. So you always make sure of that. Again, it's a similar question next time. So yeah, I will send you that link so you can see how these are calculated. So you have like what, 3 questions here? Four, 1. Okay, you have 4 questions. And yeah, you have to calculate this. I will also see what the resistivity is. And you know, AWG or SWG gauge, I will look at that as well. So yeah, any questions? Well, there are a lot of questions, but other than these that I just discussed. All right. If you guys don't have questions, that's it. I won't drag it. You already done the experiment. So this was Kira Flaws. We did the V-Stone Bridge today. Next time, obviously not meeting next week because of fall break. That's the last day of fall break, next Tuesday, and we'll be meeting 2 weeks from now. So you guys have a nice fall break, and I will see you after that.